Hi, everybody. I'm Gal, and I want to speak with you about malware representations using graphs. This talk is pre-recorded, so you are more than welcome to ask questions in chat, and I'll be happy to answer. I'm Gal Braun. I'm married to my wonderful wife, Adi, and we have two wonderful boys, Alon and Niv. I'm a data scientist at Sentinel-1 for the last 4 years, where I manually use machine learning models to try and solve challenges in the cybersecurity world. So a little bit about Sentinel-1. We're a cybersecurity company in hypergrowth with thousands of customers worldwide. We have several offices, most of R&D located in the Israel office. The company established as a next generation antivirus, which was focused mainly on endpoint protection on all the main platforms. We have different products like static file AI detection, network visibility, and so on, and an XDR, which is based on our crown jewel model at the behavioral AI, which I will elaborate later about improvements that we are working on in this model. There are also different kinds of services like our MDR, which is a service of analysts that sits inside Sentinel-1 and can manage customers' sites if they want. Okay, so the last concept that I want to mention is the storyline. The engine, Sentinel-1 agent, it monitors all the different processes, files, and different entities inside the computer and log everything everything that happened. The very cool thing that he does is to segment the events into different contexts, which they call storylines, which contain all the different data about the events. In the case of some incident, it will be possible to understand exactly what are the problematic processes and remediate them in one click and go back to normal. So about a year ago, someone in the company approached me and asked, is it possible to do a behavioral similarity based on our storylines to detect new malwares? And that's what led me to the work on the project that we'll shortly mention. But first, let's go on a short overview about what is malware analysis and how the challenge is tackled over the years using machine learning. From the book Practical Malware Analysis is the art of dissecting malware to understand how it works, how to identify it, and how to defeat or eliminate it. When analyzing a malware, there are two main approaches to try and understand its nature. The first one would be a static approach, which would take a file, for example, a portable executable file, which is a Windows executable. Just as a side note, not all malwares, of course, coming from PEs, and there are other executable files and command lines, but it's the outer scope of the stock, and from now on, we'll consider only portable executables. We can take a look under the hood of the binary file before executing it and try to understand what's the nature of it, what is different attributes. For example, what are the DLLs that it is importing, what is the checksum of the file, and which kind of section this file is built from. The more sophisticated analysis, which will contain some kind of disassembly of the code or reverse engineering process to try and understand what is the file will maybe try to execute when executed. The other approach will be a dynamic analysis, which means we want to first execute the file and see what actually did and how it affected the system. So there are several ways to do it. The first one is to create some virtual machine, some safe environment for the malware and execute there, and just watch manually what's going on there with various tools like Process Explorer to understand the different what's going on in the processes, or for example, Red Shot to understand the changes in the registry keys. Another way is to use a sandbox. For example, a Coco sandbox is very popular in a lot of papers around machine learning to detect malware using it. It will execute the malware and create a detailed report of exactly what the malware did. And lastly, we can use a debugger or, that's we can understand, like run the commands the malware wants to do, like step by step, and not just overview the code and trying to understand what's going on, actually running, executing the code and see how the variables are changing and so on. When we speak on machine learning application to try and classify malwares, there are several known methods used when trying to handle a binary file. The first approach will be a regular feature engineering from like the domain experts. In this case, which will be some security researcher that will explain what the security researcher is looking for when he looks on a sample, on a malware sample. Can go again from, as I explained, like static features, like about the structure of the file, if it's resources, is it compiled in debug mode, some properties about the sections, about the bytes inside, and also it can be like dynamic features. For example, what actually API calls called, some information if the sample is packed. So for example, if then unpack itself, and then we can extract some information about it. And again, also what actually which file changed, what's the values, new values in registry values, and so on. The other side, like in many other domains, we will take the raw data and in some format and give it to the model to try to understand exactly, do some like feature learning and let it understand by itself what is the interesting information. One method which is inspired from the advancement in computer vision models, which at first made me raise an eyebrow, but apparently it works, is to take the binary file, parse it to lines of bytes, and each byte is then transferred to a pixel where the value of the byte is fixing a color shaded between black and white. And voila, we have an image that represents the binary file. Then we can take the image and just insert it to a well-known network like VGG or ResNet. We can create a network from our own. Basically, you can use any normal pipeline of convolutions and pooling layers. And here's, for example, as a figure from a paper referenced below. And you can see like different malware families that actually we can see like different patterns inside the images. And so other approaches will take inspiration from evolutions in the NLP domain. We can take a portable executable API file, binary file, and again extract the raw binary from it. But this time we can try to disassemble the binary in a process called surprise disassembly, and try to understand what is the code that hides behind this binary. Assuming that we made a good job, we have different information here. We can the addresses, we can extract the different instructions and the different arguments, and then we can handle it as an NLP model with a spatial characteristics. There are different models that are trying to understand code. So here's you can use it here, and we can extract from. You can try to extract like simple features like counts and n-grams. So some more sophisticated approaches. For example, here there's a paper that extracting the assembly data and use word embedding to try and represent the different opcodes. And then get a representation of functions and overall the file in the end. And we can go what's called pro all the way. And here you can see a paper that's actually created a sophisticated transformer architecture that receive a binary file, disassemble it, and again consider it as an NLP, as a textual data. Okay, so let's go back to the behavioral similarity model that I described before. So we have a storyline, and Sentinel-1's agents generate high-level feature events, which called deep visibility events with enriched metadata about them, and describe exactly what's going on in the computer. For example, it can be simple events from process creation, file deletion, registry keys, modification, so on, but it can be also high-level events that I can't elaborate too much, but they represent some deeper understanding of the status of the system and it allowing us make smarter decisions. So we want to take the storyline, pass it through a model, and get some numeric representation of the storyline. Hopefully, if we'll do it again and again and again, we'll get the representation of our storylines. And if those representations are actually meaningful, which means similar storylines, we'll have coupled similar vectors, and then we will reach our goal. Okay, but how can we get there? And here started my affair with graphs. So what are graphs? So if you did any STEM degree, you've probably seen this definition before. Graph is defined as two sets, a set of vertices or nodes, and a set of edges. Let's talk about how can we use graphs to represent malwares. I'll show you two approaches. Of course, it's just my journey inside the graph world. I don't claim that those are the best models, the best approaches, but it's just my personal experience with working on them, and I hope you can gain from it yourself also. So first one will be a dynamic approach using dynamic events happen inside the computer. I use specifically Sentinel-1's DB's events, but of course you can do the same with different events like raw ETW or high-level products that are doing similar event collections from a machine. And the second one would be static approach using call flow graph. So I will elaborate later if for whoever not familiar with the concept. So as I mentioned in the start of the talk, we have what called a storyline that behave like some kind of context manager for the events and entities that belong together. So here's an example for one, which I used Bokeh to visualize it. Here, each circle represents some entity, like a process or a file, and each line represents an event. So as I said before, straight from the start, beside considering simple feature engineering approaches, the idea to try and create a graph-based model was pretty straightforward. Again, Sentinel-1 has what's called MDR service, which we call vigilance in our company. As part of their day-to-day job, they go through threats from managed customers and verify which of them are real threats, true positives, and which are false alarms from false positives from other models that are going on inside the agent. So what I did was to collect those true positives and false positives from the vigilance service, and I have their labels, and I extracted their events saved in our systems. And here I have a data set that I can play with. So as I mentioned, I decided to go with the concept of graphs. I decided to go with the concept of graphs to check how well it works. So I needed to extract the metadata from our events and create graphs on them. For that, I used NetworkX, and then I had a data set of graphs. I started to do a simple research on how can I do a whole graph classification task. And one model that seems to be simple to start with was a method called graph2vec, which is basically like a doc2vec, but for graphs. For whoever doesn't familiar with doc2vec model, it's an extension of for2vec that suggests that besides the word embedding metrics, we can add a second metrics that represent our documents representation in the new latent space and that we're learning and be optimized during training. The other thoughts about a neat idea that a graph is constructed from a subgraph is a similar way that a document is structured from words. When we talk about word embeddings, the words are showing again and again, and we then learn the contextuality. And it's very simple to get some single representation of a word. It easily can be hashed, and we can give it a special index and to extract from the embedding metrics. But how can we hash a graph? on a subgraph. We need somehow to give each one of the graphs an index, and if the subgraph showing again and again in our graphs, we need to know where it's shown in the inside the embedding matrix. So the authors then turn it to what called graph kernels, which there are many kinds of them, but the task is similar. We want to insert a graph and create some vectorized representation to allow some further analysis on it. One of those kernels called Weisweiler-Lehmann kernel. How it works: here we have, for example, two simple graphs. We want to extract a representation, and we can see that each node has some label. The basic idea is that each node will compute a new label that we will use to represent him and his neighborhood. As you can see, for example, this 4 is neighbor with 1, 1, 3, and 5. And here's the new labels, label that we get. Interestingly, to see, for example, you can see those two 5s. In both graphs, they have exactly the same neighborhood, 3, 4, and a 2. And they have the same label. And now we can see that in the representation of the subgraphs in the right, they have the same new label. Next, the new neighborhoods labels will get labels, and we basically can do this process again and again to represent the neighborhoods from different depths. It's a hyperparameter that can be optimized to our case. And finally, we can see the representation of our graphs here as count of the original labels and the new high-level subgraphs created. Okay, cool. Now the next step I did is I used some implementation of Graph2Vec and extracted the embeddings. I extracted the embeddings and used TS&E for dimensionality reduction, and here are the results. The orange ones are the false positives, and the blue dots are the true positives. So yes, the results are far from perfect. You can see many places that got mixed labels, but I was very excited from the solid cluster that you can see around here and around here. I might going on the right direction. So the time it took me to get to some POC results was pretty quick, but after deeper thinking about the subject, I got to the conclusion that using Graph2Vec to this specific project will be suboptimal. Firstly, the algorithm is transductive, which means if I get new graphs, I need to return all the embeddings from the start. And with the latency training, the embeddings again and again was not good enough in this scenario. Secondly, Weisweiler-Lehmann kernel working with a single label. And I already thought about different features that I want to add to my graph, stuff that can help me, like processes, command lines, path files, registry keys, information about the entities and events. Both of the issues can be solved with some complicated settings, but I decided to search for a different way. And then I got a revelation. A different popular approach, which gaining a momentum in recent years, is graph neural network. There is a lot of theory behind those models, and there are countless of variants and papers that suggest a new architecture, but let's just go over the main concept. Graph neural networks trying to do for graphs what two-dimensional convolutions and pooling layers did for images. Basically, we want to understand very similarly to what the idea of Weisweiler-Lehmann kernel to understand each node and edge and what's the attributes of their neighborhood. The process, often called the message passing and constructed from 2 steps, aggregate and update. So just to have enough understanding of what's the concept, let's look at a few definitions. So we want to calculate the new hidden states of node V in layer L. First, we want to collect information about the neighborhood of node V. So for every node U that's connected to V, we want to aggregate all their messages. So a message can be defined in several different functions, but it's basically a function that receives 3 values: the hidden state of V, the hidden state of U, and the hidden state of the correct edge. And do some aggregation about it. And after we have aggregate states from the neighbors of V, it's time to update it. And here again, there's an update function. The update itself can be various function again, but basically it needs to get a hidden state of V and a new message we created from its neighbors and extract new hidden state. Okay, so here's just a neat visualization to demonstrate the process. We have a graph, and this is the initial states. Let's take, for example, the node number 2. Here we'll take all of its neighbors, the initial state, and aggregate them, and then we add his initial step also, and we create some update hidden state, and we do it again and again for different for all the nodes that have ingoing edges, and then we can get some do the same again and again and get some new representation. Sorry. Okay, so there are many different libraries that we can use for GNNs. I chose to use DGL. I found it very rich in functionality. It works in a high level above different backends like PyTorch, TensorFlow, and MXNet. And they have a wonderful documentation, many examples that explain how to use it, and also a very live discussion forum. It's very active. Okay, so unfortunately, because of legal and IP reasons, I can't elaborate more about the architecture and performance of the model, but I can just say it improved results dramatically. But I did want to show you more. So as I mentioned earlier, I wanted to add another scenario, this time based on static analysis, which is not based on current product or model that we're adding to Sentinel-1's agents. So I decided to play with a example of a malware family classification. That means I downloaded thousands of variants samples from 5 different malware families. Specifically, these are the families, and I decided to use graph statically to try and classify the family for test set examples. To do so, I decided to use control flow graphs. So control flow graphs is a way to represent code of a binary file. It's going to and to understand which part of code is relevant to which part. I mentioned it before under advanced static analysis. To extract the control flow graph of the samples, I needed to use some parser. The go-to tool to do advanced static analysis is IDA Pro, a very known disassembler and debugger by X-rays, and it got a lot of functionalities, and probably if you are a senior security researcher, you open it more than once or twice in your life. The problem is that I'm a data scientist and not security researcher in my profession, and my reverse engineering days were slim to none. And also we are in PyCon, so there must be some package to extract, to help me extract control flow graph with pure Python. It doesn't have to be a perfect one, it just needs to work. So I went to Dr. Google and searched for a proper package, and there was some excellent suggestions, but amazingly I discovered Anger, which is a Python framework to analyzing binaries. I went to the documentation, and here we go. They allow you to extract control flow graph from binary file. And a major advantage with Anger that it returns control flow graph straight in a network X graph object, which is awesome. The process of extracting the control flow graphs is pretty simple with 2 lines of codes. And here we go. We have a network X object that represents the control flow graph. And this is how it looks. Each node gets information about the relevant block inside the control flow graph, for example, and very importantly, the assembly code. I decided to extract from the assembly code the counts of each extraction, how many from each type of instruction there was in each node. Just here's a list of possible instructions. Of course, feature it's a very naive feature. We can do more sophisticated stuff. Even n-grams will probably will give me better results, but I decided not to put too much effort on this model. So after defining the features and extract the graphs, I needed to define a model. I went straight to the tutorial of DGL for graph classification and took the example from the documentation as is. Here you can see we have two graph convolution layers with rel between them. And the way to get a final vector that represent the whole graph together is just an averaging of all the evident states of the nodes after the two convolution layers. And here we can see the representation of the graphs. In the left, we can see a scatter plot where the color is represent the different families. And in the right side, you can see the distribution of the training and training set in blue and test set in orange. Now I took the training set and I trained a k-nearest neighbors model and used the test set to check the performance. Here you can see some confusion metrics normalized by rows, where we can see two malware families that were predicted perfectly, and some were better and some were horrible predictions. Here we can see that this one is the one here, the green ones. I kept this question to the end, but I think it's one of the most important one in this talk. Is the representations meaningful? The model learning how to split the data set, but it doesn't mean it learns what samples are more similar to each. Let's assume we have a binary data set. We can have a decision boundary here. The splitting is perfect between the classes, but we can see the most close sample to the samples here, and the boundary is from the other class, located in the n-dimensional space. And it might be, the location here might be arbitrary. Okay, so there's a whole field around the issue which called similarity learning, and sometimes called metric learning. Of course, I won't be able to cover it correctly, but just want to give you a small taste of how to handle these situations. Popular solution for learning the embedding with consideration to actually which sample is similar to which is a Siamese network. So coming for face detection paper, the idea is pretty cool. We want to take a network that learns some representation and stop when it gives us some representation of the image, and we execute it twice for two different images and get different representations. If the same person in the two images, we want the distance between those representations to be small. If different person, we want the distance to be large. So we optimize the network parameters, so it will try to learn to make two images more or less similar. This was very shallow explanation about the notion of Siamese network, and I apologize for it. But now we can replace the images with graphs, and the second convolution, the two-dimensional convolution to graph neural networks, and we have a graph Siamese network. And modify the model to execute the training set again. And I got better results also from this two-dimensional representation. Here's the comparison between them, and also from in the confusion metrics. As you can see that here the new result, this is the former result, and the results are better. So for summary, graphs are awesome. Thank you very much, and hope you'll enjoy the rest of the conference.